This is section 17 of the ACT Math Manual, Quadratics, section 17, Quadratics. This is page 125 of the Math Manual, again, section 17. Quadratics, factoring, and FOIL. You are going to see on every single ACT several questions that deal with these concepts, these related concepts of quadratics and factoring and foiling. You need to know the information in this section very, very well. You need to be very proficient with it. If you are not, you, number one, need to watch this video and make sure you understand everything. You may also need to do a bit of extra work on your own. And if you are working with a tutor, you can ask him or her for some advice as to what additional exercises you can do to strengthen your quadratics, factoring, and foiling skills. So first of all, let's start with recognizing quadratics. Quadratics in the standard form look like this: ax squared plus bx plus c. You very frequently will see the equation being equal to 0. That would be the quadratic equation. A quadratic function would not have the equal 0 at the end. If you wrote that in pen, I apologize. So again, the standard form of a quadratic function is ax squared plus bx plus c, and the factored form will look something like this: x minus r1, x minus r2, something like that, where r1 and r2 are your roots. But you need to be familiar with these two forms. The standard form is probably the more important one. We are going to work in both of these forms. In fact, that's what we're going to do right now. So in terms of factoring quadratics, students run the gamut when it comes to factoring abilities. Some students are perfectly fine with factoring. They can look at a fairly simple quadratic and have it factored in a matter of seconds. Other students are either rusty or never learned how to do it well, or lack confidence. Again, you're going to need to be able to do this fairly quickly, and there's several ways that you can factor a quadratic. Trial and error is one way. There are some very systematic step-by-step methods that you can use to factor them. Remember, you could also use the quadratic formula if you needed to, although that's probably the least beneficial, or I should say least appropriate method on the ACT. There are also some calculator programs that may help you factor, and we'll talk about that in a moment. For right now, I'm going to do, since most of these examples are fairly straightforward and fairly simple, I'm going to actually do these the regular old sort of trial and error way. So by the way, I would suggest that you actually run through examples 1 through 4 on your own and try to do them on your own before watching me do them, to see how confident you are with these things. I'm going to go ahead and jump into them right now. So in example 1, I know that I have two x's in these positions here. That will produce the x squared when I FOIL or distribute, and I know that I have to have opposite signs because these two last terms, when I'm foiling or distributing and I do those last terms, I know I have to get a negative 18 here. So now what I am looking for is I am looking for two numbers that will multiply to give me this negative 18 and that will add to give me this negative 3, and it should be pretty clear what those are. It's going to be a positive 3 and a negative 6. And when I do this, I always do want to just check to make sure. So I'm going to FOIL this back through. So the x times the x will be the x squared. The x times the negative 6 will be negative 6x. The 3 plus the times the x will be 3x. And the positive 3 times the negative 6 will be negative 18. So indeed, I do have x squared minus 3x. That's what negative 6x plus 3x is, minus 18, and I get back my original quadratic. So factored form here would be x plus 3 times x minus 6. Now, for example 2, in order to factor example 2, I first need to get this into standard form, which would involve taking that 36 over to the left. So now I have n squared plus 12n plus 36. And I'm going to do the same thing here. I'm going to fill in the n's in my first position. That's how I will produce the n squared. Now I need two numbers that multiply to 36 and add to give me a positive 12. If it's not clear immediately what those numbers are, remember you can always start listing the factors of 36. 1, 36, 2, 18, 3 and 12, 4 and 9, and then we have 6 and 6. So indeed, it looks like this pair right here is the one that's going to multiply to give us 36 and add to give us this 12. So it looks like we need two positives here. Both this sign and this sign are positive, so we need two positives. So this guy actually factors into n plus 6 squared. And again, I would FOIL that out just to make sure that it does work, but it does in this case. Now, example 3, fairly common that you will see what is known as a difference of squares. A difference of squares on the ACT. Why is this called a difference of squares? Well, number one, it's a difference because when we're subtracting, we produce a difference. And it is a difference of squares because both a squared and 25 are perfect squares. They both have basically very simple square roots. So when we have a difference of squares, they always factor into something that follows the same pattern. Basically what you're going to have is you're going to have your two sets of factors. You're going to have the square root of the first term, so the square root of a squared. You're going to have the square root of the second term, so square root of 25, and then you're just going to have 1 plus and 1 minus. Most students, again, are fairly confident with that. They do remember how to factor a difference of squares, but that's how you do it. In example 4, again, remember I need to get this into standard form before I factor it, so I need to get a 0 over here on the right. So I'm going to go ahead and subtract the 2. Now I have 2x squared plus x minus 3 equals 0. And again, I'm probably just going to go ahead and do this one by a little bit of trial and error. I know I need a 2x and an x, and then in order to produce this negative 3 here, there's only two factors. 3 is prime, so remember there's only two factors. It's either that there's going to be a 1 here and a 3 here, or a 3 here and a 1 here. I do know I need opposite signs. I need 1 plus and 1 minus, and that's because I have this negative 3 here. So actually, let me see if this works. This is going to be 6x or negative 6x. And then plus x. So again, it's these guys. So there's the 2x squared. Then these guys is going to be negative 6x, and then plus 1x. Well, that's not going to work. That's going to produce a negative 5x in the middle. So let me actually switch these around. Let me do a little bit of erasing here. And let me put the 1 and the 3 in different positions. Let me put the 3 here and the 1 here, and let me see what happens. So now I have 2x squared, then I have negative 2x plus 3x. Well, negative 2x plus 3x, that's going to give me what I need. That's going to equal the positive x, which is exactly what I have here in the middle. So 2x plus 3 times x minus 1, that's going to be my factored quadratic. Now, in terms of, I'm going to get rid of some of this stuff, make this a little cleaner. Now, in terms of other ways to do this, again, there are multiple ways to figure out how to factor. So if you have a method that works for you, that's perfectly fine. Go ahead and use it. I will say that on most of the TI calculators, you're going to either be able to get a program or use one of these apps. We actually have used this app, PolySimult 2, in a previous video. We can use this to find polynomial roots. I'll show you in a second how this is going to work. But remember, polynomial roots is basically finding your zeros. The calculator tells me to press any key, so that's what I'm going to do. Polynomial root finder, that's the one I want. So when I get to my polynomial root finder setup, Order is just the degree of the polynomial, and in this case we have a degree of 2. We have a quadratic, that's the section that we're in. So I'm going to keep order 2. I'm going to keep this in complex mode rather than real mode. In other words, I'm going to tell the calculator, give me complex roots if we get them. We're not going to get complex roots here, but I am going to put it into complex mode just in case. And then fraction, normal, float, degree, those are all fine. I'm going to hit the graph button, which is my next tab. See this little tab up here says next. That indicates that I should push the graph button. So now what I'm going to do is I am going to enter my coefficients. The A2 is the coefficient in front of the quadratic term, the squared term. The A1 is the coefficient in front of the linear term, the term that is x to the first. And then the A0 is the constant over there at the end. So basically the A2 corresponds to my, from the standard form, the A2 corresponds to my A, the A1 corresponds to my B, and the A0 corresponds to my C, my constant. So I'm going to go ahead and enter what I have here from this standard form. So I have a 2, I have a 1 in front of my x. Remember, plus x is the same as plus 1x. And then I have a negative 3 for my constant, negative 3. Now what this is going to do when I hit solve, which again is that graph key, this solve tab indicates that I need to hit the graph key. What I get are, I get my 2 roots, my 2 zeros. So basically my 2 zeros are x equals So what I get here is I get my 2 zeros. The calculator has produced my roots. Remember, this app was called the Polynomial Root Finder. Roots are the same thing as zeros. So what those two values tell me is that x equals negative 3 halves and x equals 1. Now, if you are proficient in working from your zeros to your factors, you would know that when we have a 0 of x equals 1, that means we have a factor of x minus 1. And that is because if one of our factors is x minus 1, and we want to know what the 0 is that corresponds to that, we set x minus 1 equal to 0, we add 1 to both sides, add 1 to both sides, and we get x equals 1. So basically we're just going in the opposite direction. We're going from our 0 to our factor instead of from the factor to the 0, which is the more common direction. And then this one here would be x plus 3 halves. And you may or may not remember from math class that if you want to clear away this fractional value over here, you can actually distribute through the denominator of this fraction. So if I distribute through a 2, I get 2x plus 3. And that is the other factor, 2x plus 3 and x minus 1. Again, if you are a little bit shaky on this stuff, you're going to need to practice. You're going to need to work with your tutor to make sure that you are solid, and whether that means doing it the school way or doing it with the calculator app or a calculator program, you're going to need to get good at this. Now, a higher degree polynomial, so obviously this is a quintic, I suppose, polynomial. This is not a quadratic. You will have to sometimes factor higher degree polynomials. The first step here would be to pull out the v that is common to both terms. So we are left with v times v to the fourth minus 25. And then some of you may recognize that what we have left in parentheses is actually a difference of squares. The square root of v to the fourth is v squared, and the square root of 25 is 5. So we follow that same pattern that we talked about before for difference of squares. We put the square root of the first term in these first positions, we put the square root of the second term in these positions, and then we just have a plus and a minus. So we end up with these. That was not a minus, that was actually a plus. Who put that there? So we end up with these three factors, v squared plus 5, and v squared minus 5. And yeah, that's how we factor that guy. Examples 6 and 7, again, you might want to try these on your own before you watch me do them to test your efficiency and your proficiency. So in examples 6 and 7, we are actually not going to factor these in the typical way that we did up here in examples 1 through 4, where we end up with a set of parenthesized factors. In these quadratics, we actually can only pull out like terms or pull out the greatest common factor. So for instance, common to both 4x squared and this negative 2x is a 2x. I can pull a 2x out of these two terms, and then I have to figure out what I would have to put in these two positions so that when I distribute that 2x back through, I end up with this expression. And what I would have to put there is a 2x and a 1. And indeed, I can just check this out. 2x times 2x is going to be 4x squared, and then the 2x times the negative 1 is going to be the negative 2x. So again, I pull out the 2x, and I am left with, inside parentheses, a 2x and a negative 1, or 2x minus 1. So the two factors of this particular quadratic are 2x and 2x minus 1. Now, in terms of this number 7 here, again, these two terms have a bunch of things in common. They have a 3 in common. They have an a in common, but actually we can pull out the highest common exponent here. And this a squared, this a to the 4th, well, a squared and a to the 4th have a squared in common. And then the b and the b cubed only have the b in common. So I can only pull out the b, and then left in parentheses, in order to get back the 3a to the 4th b, I just need an a squared here. And indeed, when I multiply these two guys, I will get 3a to the 4th b. And then in the second position, I need a 2, because that's what will produce the 6 when I multiply the 3 by the 2. So that will produce the 6. The a squared, well, I already have that here, so I don't need any a in this term. But I do need a b squared in order to, I need a b squared here, in order to produce this b cubed when I multiply by this b. Now again, I'm just going to say one more time, this video is really designed just to recap or refresh some of these concepts. If these concepts are very weak for you, if you do not remember them at all, or you feel like perhaps you weren't even taught them at any point, you are going to need to figure out somehow some way of getting these down cold. Now, number 24 really just tests the stuff we were just talking about. So they are asking for, again, if you want to pause the video and try this on your own, by all means do so. So they're asking for a polynomial factor of this guy. Again, I could do this using the calculator. In fact, I think I will do it that way. First, I'm going to do it the regular old factoring way. So I'm going to write my two sets of parentheses. I know I need x's in this position. I know I need opposite signs because I have a negative here. So when these two guys are multiplied by each other, I get a negative. So I need 1 plus 1 minus. And then I'm looking for factors of 15 that also add to 2. I'm going to actually write those 115, 3, 5, and it looks like those two will work. What do I need? I need a negative 5 and a positive 3. That will multiply to give me the negative 15 and will add to give me the negative 2 coefficient here. So I need the 3 here, the 5 here. I'm going to very quickly distribute this back through to make sure that I did get it right. I'm going to FOIL, so that's x squared. This is plus 3x minus the 5x, that's the inner guys, and then the last guy is negative 5 times positive 3 is negative 15, negative 3 minus 5 is negative 2x, and indeed I did get what I need. So these are my factors, x minus 5 and x plus 3, and I see an x plus 3 right here, just in a different order. So that is one completely acceptable way to do a question like this. Another way to do this is to, again, use the calculator. And I'm going to actually show you on this one. So there is a program floating around out there. If you are working with one of our tutors, you might already have this program. Let me get out of here. So there's a program called QuadForm, or QuadNew is another one. that's a little more robust. But in quad form, it's just asking us for our coefficients, our a, our b, and our c, which is our constant. And in this case, our a, which is the coefficient in front of this x squared term, is 1. So I'm going to hit 1, enter, and then -2 is the coefficient in front of the b, and then -15 is the constant. I'm going to hit enter. So what this tells me is that my roots are x equals 5 and x equals -3. And remember, just like we did on a previous example, we can get from those roots, those zeros, to the factors. If 5 is a 0, that means x minus 5 must be a factor. And if -3, is a 0, that must mean that x plus 3 is a factor, because 5, a root of 5, a 0, 5, comes from x minus 5, that factor, and a root of -3 comes from the factor x plus 3. So in this way, we have just used the calculator program to get our zeros from which we can get our factors, and again, we saw that the answer was x plus 3. There are other ways to do this question. I would say those are probably the two easiest ways to do them. If you have watched the VITA video or gone through the VITA section, you will remember that I said that when you have variables in the answer choices, but the question is asking for a polynomial factor, you have to be careful of doing the VITA. The VITA sometimes will fail on questions like this. So I would steer clear of VITA on any question that is asking you for polynomial factors. Now on to foiling, which you have seen me do a couple of times already. Again, most students are fairly confident with foiling, so you might want to go ahead and run through examples 1 through 5 really quickly on your own, and then check back with me after you restart the video to make sure that you got these right. So this is where we go from factored form to foiled form. So we are expanding, or we are distributing. So x times x is x squared, and then we go x times -5, which is -5x, and then we go -4 times x, which is -4x, and then we do -4 times -5, and we get 20. So first terms, x times x, outer terms, x times -5, inner terms, -4 times x, and last terms, -4 times -5. And we produce these 4 terms here. We can combine the middle terms because they are like terms, so we get x squared minus 9x plus 20, and that is our standard or foiled form. Over here, this is 3x plus 6 squared. Now, whenever I see a squared on the test, I actually like to just write the factor again so that the foiling and the distribution becomes a little bit simpler to do, a little bit more visual. So 3x times 3x is not 3, so I'm going to get rid of that. It is 9x squared, and then the 3x times the positive 6 is 18x. The inner terms are going to be exactly the same. 6 times 3x is 18x, and then the last terms, the 6 times 6 is 36. So what do I end up with? I end up with 9x squared plus 36x plus 36. So that is how we foil that one. Now, keep in mind, some students will look at this and say, okay, but I can just divide through by a 9 to clear away some of these coefficients, or to reduce some of these coefficients. Yes, that would be true if you had an equal sign and then you had another number over here. You could indeed divide the entire equation by a 9. But if you simply have an expression, if you do not have this equal sign here, you cannot divide through by 9, or else you would be changing the value of that expression, and you don't want to do that. You could factor a 9 out. You could do something like 9 and then in parentheses the x squared, blah, 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 blah. But for right now, there's no reason to do that. But keep in mind, you cannot simply divide through by 9 unless you're dealing with an equation rather than an expression. Some of you may recognize on number 3 that this is how we factored a difference of squares, and indeed this will distribute through to x squared, that's first terms, last terms plus 7x, inner terms negative 7x, last terms minus 49, and we have that difference of squares that we talked about before. X squared and 49, both squares. We are subtracting them. We have a difference of squares, and indeed that would factor into the x minus 7 and x plus 7. Now, number 4, similar, obviously, in structure to number 2. And remember what I said. I said I'm going to go ahead and write down the other factor instead of just keeping that square there. So first terms, m squared. Outer terms, negative mn. Inner terms, also a negative mn. And the last terms here, negative n times negative m, would be positive n squared. So I get m squared. These are like terms. This is negative 1mn minus another mn. So that's going to be minus 2mn plus the n squared, and that is my FOILed form. This one gets a little bit ugly, but fortunately we have another difference of squares here, so some things are going to cancel out. So let's take a look at this. First terms is 4x squared, and outer terms is going to be 6xy cubed. And then the inner terms here is going to be negative 6xy cubed. And then the last terms are going to be negative 9y to the 6th. Don't make the mistake of doing y to the 9th. Remember, you add these exponents. You do not multiply them. These two are going to cancel out, and we end up with 4x squared minus 9y to the 6th. So yet again, another difference of squares. Simple FOIL questions like number 16 are pretty much free points on the ACT. Almost every high school student should be proficient enough with foiling and factoring, basic foiling and factoring, that questions like these should be very simple. The only danger in these questions really is, for most students, is careless mistakes, which usually involves forgetting to distribute or deal with some negative in the appropriate way. So as long as you take these one step at a time, make sure that you're being very systematic. They shouldn't be too difficult. So they want to know which of these answer choices is an equivalent expanded or FOILed form of these factors. So let's do this one step at a time. So first terms, 2p times 3p is 6p squared. Outer terms, 2p times negative 5 is negative 10p. Inner terms, 4 times 3p, that is positive 12p. Last terms, 4 times negative 5 is negative 20. These two guys are like terms. They can be combined. Negative 10p plus 12p is 2p. So my final expanded form is going to be 6p squared plus 2p minus 20, and that is answer choice K. 6p squared plus 2p minus 20. Could you have used Vita on this question? Yes, absolutely. You could have said p equals, let's say, 2. Therefore, this first factor, 2p plus 4, would be 8. And this second factor, 3p minus 5, would actually be 1, 6 minus 5. So we would get 8, and then we would go to the answer choices looking for 8. So yes, you could do this using Vita, and it would be fairly simple, but if you do know how to distribute algebraically, that's probably the route you want to go. It might be slightly quicker. Matching up parts. So on some quadratics questions, all you are doing is playing a matchup game. You'll be given something in factored form, and it will be equated with the standard form, and you will need to know what the x, the b, and the c are once we FOIL out these two factors. So as an example, we'll look at number 6. If you do want to try it on your own before you watch me do it, go ahead and pause the video. I'm going to go ahead and do this now. So again, foiling here, I get x squared. X times the positive 4, that's 4x. The negative 3 times the x, that's negative 3x. And then the negative 3 times the positive 4 is not positive, sorry. That's going to be negative 12. So this foils out to x squared plus x minus 12. Now remember, they were equating that with standard form, ax squared plus bx plus c. And what I should be able to see is I have a coefficient here in front of the x squared term, corresponds to the a here in front of the x squared term. I then have a coefficient here, I'll do in blue, in front of the x term, that corresponds to the b here. And then my constant, the negative 12, corresponds to the c over here. So what I need to do is I need to simply figure out, okay, well, the coefficient in front of the x term is 1. That corresponds to my a. So my a is 1. My coefficient in front of my linear term, I believe I just said in front of my x term, but I meant my x squared term, I apologize. My coefficient in front of my x term, the linear term, the x to the first term, is also 1. So that's my b. That corresponds with my b coefficient over here. So that's also a 1. And then my constant is this negative 12 here. So my c is negative 12. So again, we're just expanding or foiling and then playing a matchup game, figuring out which of the coefficients in this match up with the a, the b, and the c. So in example 7, very similar. We've got 2x minus 5 squared. So I'm going to do 2x minus 5 times 2x minus 5. That's going to be 4x squared. This is going to be negative 10x minus a 10x, so negative 20x, and then plus 25. And that equals, as they tell me, just like in the previous question, ax squared plus bx plus c. So again, remember what we said. We said that this 4 and this a correspond. We said that this negative 20, which is in front of the linear term x, and this b correspond. And then I'm out of good highlight colors, so let me try something different here. That's ugly. Wow, those are ugly colors. Let's do this. This is, yeah, it's not too bad. So our C corresponds to the 25. So what I know is that my A is 4, my B is negative 20, and my C is 25. Now, examples 8 and 9 are definitely the toughest of the bunch, and these will indeed, these are good representations of some of the tougher matchup questions that you will encounter. So let's take a look at example 8. So again, we're going to go ahead and FOIL this out. So x plus t squared is x plus t times x plus t, and that's going to equal x squared plus 2xt. If you need to do this one step at a time, that's perfectly fine. I'm going to combine some steps here. X squared plus 2xt plus t squared. Now, one tricky thing here is a lot of students will indeed write out this middle term as 2xt. I would recommend putting the x at the end. So in other words, I'm going to come over here and I'm going to write down x squared plus 2tx. Remember that multiplication has the commutative and associative properties. So when I'm multiplying 2 times x times t, I can write that however I want. I can write it 2tx, 2xt, t2x. It doesn't matter. I can move these terms around however I want. I'm putting the x at the end so that, I'm going to finish this up and do the t squared. I'm putting the x at the end so that it becomes clear that this 2t is actually my b. That 2t represents the coefficient in front of this x term. So when I write the other side of the equation, which I'm going to do now, that's the other side of the equation that they gave me originally, I should be able to see that this 2t and this 8 are both my b's. They are the matchup here. The 2t and the 8 match up. They are both the coefficients in front of the x term. So now what this means is that 2t equals 8. These two equal each other. 2t equals 8. We divide by 2, and we get that t equals 4. So that's how we do that one. We find that the 2t and the 8 are the b's that match up, and then we have our t value. This one down here also a little bit more challenging, a little bit more difficult, but similar to number 8 still. So we're going to do x minus r squared. We are going to distribute, we're going to FOIL, so that's going to equal x squared minus 2rx. Remember what I said, I want to put the x at the end there. So I'm going to do minus 2rx and then plus r squared. Now, they tell me that that all equals x squared minus 16x plus m. Well, once again, we can do a little bit of matchup here, and we're going to do it with the b's again. We should be able to see that this negative 2r is the coefficient in front of the linear term on the left, and this negative 16 is the coefficient in front of the linear term on the right, and therefore, once again, those are our b's on each side, which means they match up, which means we can set up that equation negative 2r equals negative 16, divide by negative 2, divide by negative 2, we get r equals 8. Now, we have the r. How do we find the m? Well, we find the m very simply by realizing that this r squared and this constant m here, they match up as well. And since I already know that those are both my c's, the r squared is my c on the left, the m is my c on the right. I'm going to actually catch this plus sign in there. So they match up. Those are my c's. And since I know that r is 8 and m equals r squared, then m equals 8 squared, which equals 64. So I have my r, I have my m, and that is how I match up on that question. There's a little note at the bottom of the page that does let you know that some of these questions can be solved with the tin techniques, either Vita or Nidus, or possibly General Tin. But it is true that the algebraic solution, in other words, the stuff that we just did, tends to be the most efficient. You just have to get good at seeing what matches up with what. Now, roots of quadratics and other polynomials, you will get questions that ask about roots. You must understand that there are a bunch of synonymous terms here: roots, solutions, zeros, and x-intercepts. These all mean the same thing when it comes to polynomials. They all mean exactly the same thing. You have to understand that so that if you see varying terminology, you will understand that there's no big secret or mystery to what you're doing. If they ask you about x-intercepts, you can think of those as your zeros. If they ask you about solutions, you can think of those as your zeros. If they ask you about zeros, you can think of those as your roots. All the same thing. Anyway, have I made that point clear? These are all the same thing. Okay, moving on. Roots of quadratics. So quadratics, which, by the way, take the form of a parabola when graphed. So do keep in mind that every time you graph a quadratic, you're going to see a parabola. Whether the parabola looks like this or like this or like this will have to do with what the quadratic function looks like. But every time we graph a quadratic, we're going to get a parabola. There are three situations that can occur when we graph a quadratic. We could get a double root, which occurs when the parabola just kisses the x-axis. So if you ever see a parabola whose minimum or maximum point is tangent to the x-axis, that basically means that we have a double root and we have something in the form x plus something squared. So that is one situation. We could have the parabola just kissing the x-axis, in which case we have what is known as a double root, and we have the factored form that looks like this. We could also have two real roots, and this is where the parabola crosses the x-axis and then comes back and crosses again. And remember, it could be upside down like this as well if it was made really sad. And in this case, when we have two real roots, we have a factored form like this where our two values here are different. In this case, the two values were the same. It was x plus 3, x plus 3. But when we have two real roots, we're going to have differing values here after the x's in our factors. So what we also can have is we can have no real roots. No real roots occurs when the parabola does not touch the x-axis at all. Keep in mind, remember we did just say about 17 times that the roots and the zeros and the x-intercepts are all the same. Well, notice when we say one double root or two real roots or no real roots, we're also talking about the number of x-intercepts the parabola has. So when we say two real roots, that's the same as saying two intercepts, two x-intercepts. When we say no real roots, it means that the parabola does not intersect the x-axis at all. So those are our three types of scenarios we can run into when we're finding roots of a quadratic. Now you will need to be very proficient at working back and forth between factors and roots. If you want to go ahead and run through 1 through 7 on your own real quickly to see how you do, go ahead and do that now. I'm going to run through this really quickly. Again, I'm assuming that you have some pre-knowledge, some idea of what's going on here. So again, I'm going to go quickly. The roots here would be x equals 1 and x equals 3. The roots here would be x equals 2. That would be a double root. That's a double root. In Algebra 2 or pre-calculus class, you might have heard of that in terms of multiplicity. That has a multiplicity of 2. These guys here, so now we're going the opposite direction. We're going from roots back to factors, and we sort of did this before. So if we know that -3 is one of our zeros or one of our roots, that means we had a factor of x plus 3. And if we know that 4 is one of our zeros or roots, that means we had a factor of x minus 4. This is purely algebraic in nature. So here we have a situation where we have to find out what our zeros are from these algebraic terms. Well, there's two ways to do this. One is if it's just very obvious to you, then go ahead and do it that way. But remember, you can also just always set your factors equal to 0 and then solve for the x. So if I add x to both sides here, I get that x equals m. And indeed, if I throw in an m here for x, I will see that this factor will become 0. So x equals m is one of my zeros of this factor, or of this quadratic that corresponds to this factor on the left. And then the 0 on the right, x minus n equals 0. Add the n, and I get x equals n. So there's my other root. There's my other 0. Now, working backwards from this root to a factor, I would know that this has to be a factor of x plus 1. Since this has been identified as the only root and we are dealing with quadratics here, this would again have that multiplicity of 2. This would be a double root. Same thing down here. We are only given one root, but this is a parabola. This is a quadratic, so we know this is a double root. So this would be x plus 2/3 squared. You may remember from a previous example, I did say that we could clear this fractional term here by multiplying through by the denominator. So this would actually also be 3x plus 2 squared. That would work as well. So example 7, so if we know that r and -s are roots, we do something very similar to what we've done in these other examples. We basically just go x minus r is going to be one factor and x plus s is going to be other factor. In case you didn't know this or didn't recognize the pattern, basically what you're doing is you're just taking the opposite of this number in terms of sign and putting it after an x. So the opposite of this number would be +3. So it's just x and then a +3. And then the opposite of this one would be -4. So it's an x and a -4. It's the same thing down here. Opposite of this guy in terms of sign would be -r, so it's x minus r. Opposite of this guy would be s, so it's x plus s. So if you have a root, you can just flip the sign and put that term after an x. Now, in terms of getting from standard form to your roots, we've actually talked about this a little bit already. You have several different ways to do this. One is you can just factor the quadratic and then determine your zeros or your roots from the factors. And we saw this back on a bunch of these questions. So when we factored, let's say, example 1, well, from these factors, we could get our roots. We could get that this root would be -3 and this root would be 6. So x equals negative 3 and x equals 6. So we could factor and then find our roots from those factors that we produced. We could use the app that I just pointed out, or the calculator program QuadForm or QuadNew. We can also use the graphing window. Remember that we can always graph a quadratic, and based on that graph we can either approximate where the intercepts are, where the zeros are, or the calculator actually has a function whereby it will determine. So if I did something like, that's not what I wanted to do. If I did something like x squared plus 3x, actually I'll just graph that. So when I graph this parabola, I can see where the intercepts are. It looks like the intercepts are at negative 3 and 0. The calculator actually will find those zeros for you exactly, so you don't have to guess or approximate. That would be in the second, and then this calc menu here, second calc. Number 2 is 0, so I would hit 2. The calculator is asking me to capture the 0 that I want to find. It's basically going to ask me for a left bound and a right bound. And the reason I have to do that is because I have multiple zeros. I have 2 zeros. So the calculator needs to know which of those zeros I want to find. So what I'm going to do is I'm going to hit my left arrow until I get to the left of this 0. I'm going to hit enter, and then I'm going to capture it. I'm going to capture this 0 here by going to the right, and I'm going to hit enter. And you can see these 2 arrows now. I have told the calculator I want you to look between those 2 arrows for a 0. So the calculator knows I'm not looking for this one over here, but I'm looking for this one here. The calculator is now asking me if I want it to take a guess, and I don't. I don't want the calculator to guess at all. I'm just kidding. I want the calculator to guess. So I'm going to hit enter, and indeed the calculator gives me 0 of negative 3. So it's telling me my x-intercept is negative 3, and that point right there is negative 3 comma 0. If I wanted to find the other 0, I would give it a left bound somewhere over here, and then a right bound to the right of that 0. And you can now see I have captured this 0 between these 2 arrows where I put my boundaries. And then if I want the calculator to guess, which I do, it's telling me that 0, 0, the origin, is my other intercept. So I can always use the calculator's graphing window to find my zeros. I could also use the quadratic formula, but I would really prefer not to. And I would prefer that you don't do that either, only because it can be a little bit dangerous because of all of the different signs and squares and square roots and all that stuff, and it can take some time. Now, on a question like number 28, we'll do this with a couple of methods. Let's first do it with the calculator graphing window, since that's what we just talked about. So I'm going to go into my y equals, I'm going to hit second insert, and that's going to allow me to pop a 2 in for that was second, and then this delete key has INS above it. The INS stands for insert. So when I do that, you'll see that the cursor changes from this box, this black box, to a underline. It just changes to an underline, and that allows me to throw a number in front of another term. I don't want that 6 there, so I'm going to go back and hit delete. So now I have 2x squared plus the 6x. So this time I don't want to insert, I just want to type right over that 3x. So I'm going to hit a 6 right over it, and then remember I need to bring this 36 over to the left, so it's going to be a negative 36, so minus 36. So this is the quadratic in standard form. I'm going to hit graph. Okay, so the quadratic goes way down here. I can't see the minimum, but that's okay. By the way, this should be circle values of x. Basically, they're asking me for my roots or my intercepts. So again, this one I think I can just approximate. 1, 2, 3, 4, 5 tick marks, 6 tick marks to the left of 0 would be an x of, or a 0 of negative 6, and then 3 tick marks, 1, 2, 3 tick marks to the right would be an x of 3, so negative 6 and 3. Well, that was easy. Again, remember I could use the second calc 0, number 2, ask me for the left bound. So if I want to find this 0 on the left, I'm going to have to go to the left of that. Let's see, where is my cursor? There's my cursor coming up. So I'm to the left of that 0 now. I'm going to hit enter. I'm going to go to the right of it. I'm going to hit enter. So I have captured this 0 between my two arrows here. I want the calculator to take a guess. It guesses -6, 0, which is exactly what we came up with. So that's how we would use the graphing screen. The way that we would use probably the easiest way to do this question is to use our app that we talked about before, Polynomial Simultaneous Equation Solver. So number 2, hit enter, go to number 1. Remember, we can keep all this stuff the same for quadratics. Hit the graph key, which is next. Enter the coefficients. 2, enter. 6, enter. And then remember, my constant would be -36 because we brought this 36 over to the left. Hit solve, and boom, I have my zeros. That is almost definitely the easiest way to do this. And then the quad form program, let's get out of here. The quad form program number 2, this would also be very, very simple. 2 is my A, 6 is my B, -36 is my C, and boom, I have my roots, my zeros. Also very easy. I am not even going to attempt to do the quadratic formula because I hate it. I hate the quadratic formula. I just hate it. I'm just kidding. I don't hate it. It's just complicated. What is the quadratic formula? It is that your roots, x, equals -b plus or minus the square root of b squared minus 4ac all over 2a. That is the quadratic formula. Now, occasionally, you're going to run across a question, and I say occasionally, but number 53 at the bottom of the page is really the only question where I've ever seen this happen. Occasionally, you may run across a question where having some understanding of what the quadratic formula is and what it tells you may help you to solve a question very quickly. Before I do number 53 using the quadratic formula, I'm going to circle that. That's what they're asking. I am going to say that there are other ways to do this, which I'll show you in a moment. But one of the ways to do this is to know that if a quadratic has only one solution, what that means is that this part of the quadratic equation is 0. Because if that part weren't 0, we would have a -b plus some value over 2a, and we would have a -b minus some value over 2a, and we would have two solutions. We would have two solutions if that stuff inside the square root is not 0. But if the stuff inside the square root is 0, we would have -b plus 0 over 2a, and we would have -b minus 0 over 2a. Well, remember, these two guys go away, and we're just left with -b over 2a, and that's the same solution. That's one solution. So to summarize what I just said, it is if the stuff under the square root, which is b squared minus 4ac, this is called the discriminant, by the way. You might remember that from math class. If your discriminant equals 0, that means you only have one solution. If the discriminant does not equal 0, if it equals a positive number, it means you have two solutions. And actually, if your discriminant is negative, it means you have non-real or imaginary solutions. So I'm going to go ahead through this question using this piece of information that we just learned. So b squared minus 4ac has to equal 0. Well, remember, b squared is this -10 squared, and -10 squared is 100. Minus 4, our a is 1, so that's easy. That's just 4 times 1, and our c is our k. Our c is our k. So this is 100 minus 4k equals 0. Add the 4k, add the 4k. We get 100 equals 4k. Divide by 4. We get k equals 25, and we're done. So like I said, if you have a good sense of the quadratic formula and what it tells you, you may be able to use the quadratic formula in a question like this. The other way that you can do a question like this, there's actually a few other ways. One of the ways is you could nidus. You could just start taking these answer choices. So let's say I make k equal to 10. Well, if I go to my calculator and I go into the polynomial simultaneous equation solver, get back into this screen, well, in this case, my a2, which is the coefficient in front of the x squared, it's my a in ax squared plus bx plus c. So that's a 1. The next one is -10. And since I'm throwing in answer choice C, which is 10, and that's going in for k over here. So my quadratic, I should write this down so you know what the hell I am doing, right? So this would be x squared minus 10x plus, I'm running out of room here, give me one moment, plus 10. Okay, so x squared minus 10x plus 10. So that is what I'm going to put in here to the simultaneous equation solver. When I solve, look what happens. I do not get only one solution. So that tells me C cannot be correct. I got two solutions. If I try answer choice D, which would be k equals 20. So now my quadratic would look like x squared minus 10x plus 20. Now, cool thing about this program, I can go back to this coefficient tab, which is my zoom button, hit the zoom button, I'm back into my coefficients. The 1 and the negative 10 stay the same. All I have to do is go down here, change this to 20, hit solve, and again, I get two solutions. So I know now that that 20 is not correct. It is not answer choice D. Answer choice E, when I throw in the k equals 25, now I have x squared minus 10x plus 25. Again, I'm going to go back in here to coefficients. I'm just going to go down to this guy. I'm actually just going to enter a 25 in there, and now watch what's going to happen. Boom. I get only one solution. 5 would be my only solution. Yes, it looks like two solutions because it has an x1 and x2, but since they're the same, that's equivalent to saying that there's only one solution. So I could do this using my calculator and some other methods. There are other methods that I could do. Some other methods actually related to the quadratic formula again, but either way, whichever way you're comfortable with, you go ahead and do it that way. So that's it for quadratics, factoring, and foiling. So just to recap here, remember we said that we need to be proficient with going from standard form to factored form. Actually, we need to, first of all, know how to recognize when we're dealing with a quadratic. And by the way, I probably should have said this from the very beginning. Any function or equation that has a degree of 2 on the x and a degree of 1 on the y, so y to the first and x squared, anytime we see an equation with this situation, we're dealing with a quadratic equation. We're dealing with one of these two situations. So the recognition factor is here. We need to be able to go from standard form to factor form. We need to make sure that we go from factored form to standard form. We do that through a process called foiling. We need to make sure that when we foil, we don't make careless mistakes. That often will involve making sure that you're being very careful with your negatives. Negatives can be a little bit tricky on foiling questions. We talked about matchup questions. These questions can actually be kind of fun if you get good at them. We talked about finding roots or zeros or solutions or x-intercepts to a quadratic. We talked about what it means to have one double root, two real roots, no real roots. We talked about moving between factors and roots. We have to be proficient in going in both directions. And then we talked about some of the ways that we can find roots. We can do regular old factoring. We can use a calculator program. We can use the graphing window. We talked about some cases where the quadratic formula might come in handy, but I would say for the vast majority of students, it's pretty much completely irrelevant, the quadratic formula on this test. You probably are never going to have to use the quadratic formula, and certainly the quadratic formula will very rarely be the best way to get a question done. That is it for quadratics.